is how we're bad at the end. And then we'll start in on the mass transfer stuff on the species mass equations today, if we've got a few minutes. So remind us where we were. So we spent a whole lecture talking about equations and trying to understand this, and I'm not going to go over that again. But we got to an equation of change for the temperature, which was kind of like our Navier-Stokes equation, but for temperature. And it had all these terms in it, and they were obnoxious, right? How do we deal with all these different pieces? And so we said we wanted to simplify that. So we picked 3 cases to simplify. And the 3 cases that we picked were an ideal gas, an incompressible liquid, and a solid, okay? And this seems like a pretty good thing that covers most, I think, of the things we'll care about. Maybe you'll end up doing something complicated, but at least you'll have, more complicated than this in your time, but at least you'll have these 3 to sort of refer to as a base case. Nice to have some intuition to think about. Yes?
On the topic of more complicated, do any of these equations take into account radiation?
Radiation. So, nope. Okay,
I'm curious.
So I'm trying to think. Radiation would likely be a source term in your heat transfer, right? So yeah. So one of the things I think that's the point kind of graduate classes is to give you experience with some of these problems so that you have kind of an intuition that you kind of can run back to. That's your foundation. And then when you get something sort of more complicated like nuclear problem with radiation, you have an idea like, oh, I'm going to start with the incompressible liquid problem. And then you go, oh, and that's going to be another source term here, right? And you have a way to think about that, at least a jumping off point, right? So you have sort of this foundation and these other things that you can sort of run back to. I see that, like every discipline has their training, and it's always interesting to see. I work in really interdisciplinary area in materials and polymer materials in particular. There's people that do biology, material science, physics, chemistry, chemical engineering, mechanical engineering, electrical engineering, all these people in this area. And you'll have a problem, and it's really interesting to see the sort of classic problems that are their intuition, right? Like the physicist, it's always a harmonic oscillator or like a particle in a box. Like that's always kind of their intuition of the problem that they're running back to. Chemists, I don't know what chemists think. They're really confusing to me. But I don't understand chemistry. I've been thinking about like teaching a polymers class because I was thinking, oh, Dr. Pitt's got to retire in the next 5 or 10 years. It would be nice to teach a polymers class. And I was looking at a book the other day and I was thinking about all the polymer chemistry that I don't know. And I was like, oh man, I don't know if I could teach a polymers class. I could do all the other stuff easy. And I was like, polymer chemistry, this is like organic chemistry that I, never understood. Anyway, so I don't know where I was going with that, right? Oh, the standard cases. So anyway, so for us, like a diffusion equation hopefully becomes one of the standard things that you look at. And in the research I do with polymer field theory, for example, we end up having statistical mechanics that you can solve, but you have to solve what are these modified diffusion equations. And they're basically diffusion equations with source terms. And when we go talk to the physicists, they're always like, oh, this is like a Schrodinger's equation. Schrodinger's equation looks a lot like a diffusion equation, and the solutions are similar, and the methods that we're going to talk about sort of in the second half of the class are similar for solving the Schrodinger's equation as they are for solving this, because they're PDEs and they're boundary value problems. They often do it, say, in spherical coordinates, because that's the hydrogen atom solution. Spherical coordinates are like not that useful in transport problems, but or like for most of them. But sometimes we have spheres and stuff that are resolving that's useful. So, okay. So we talked about ideal gas, incompressible liquid. And just to remind us, so we talked about the simplification, and then Andrew asked this great question, which was like, well, how do we tell the relative magnitude of these things? And I don't have a bunch of numbers to plug in for you. I probably should do that sometime. But the way I think about this is you non-dimensionalize these into these dimensionless groups, and then evaluating these dimensionless groups tell you how important that is. And I think this is more general than the number examples, but the number examples are also useful to sort of get an intuition for them, and we should probably go back and do that sometime. But so we can look at the ideal gas one, and you end up with a Peclet number and an Eckert number. And the Peclet number, you remember, was this ratio of convection to diffusion. Yeah, convection to diffusion, okay, or convection to conduction. You can maybe remember that because the conduction at the bottom. And then the Eckert number was this guy here, which was the ratio of kinetic energy to enthalpy. We have the Brigham number, which was the relationship basically between viscous dissipation. You can think of that as mu u squared over L squared divided by, this was conduction. And so we had to divide it by the Peclet number to get the convection. And then one thing we didn't say, but you can rewrite a lot of these dimensionless numbers in terms of each other, okay? And you can rewrite a Peclet number in terms of the product of the Reynolds and the Prandtl number. Okay? And these are both numbers that we've encountered before, back when we were first talking about diffusivities and ratios of diffusivities. So this is the ratio of the momentum diffusivity to the thermal diffusivity. Okay, that's what the Prandtl number is, and the Reynolds number we know very well, so that gives you a Peclet number there. You could also, instead of writing this as the Brigham number divided by the Peclet number, you can write this as the Eckert number divided by the Reynolds number. So that's kind of interesting too. So you can maybe see a relationship a little bit between, you know, the dimensionless numbers there, but I don't know too much to take away from that. Okay, so the last one that we didn't get to yet was solid. Okay, and we had this relationship rho c sub p naught dt dt, where these are partials here equals k grad squared t. Right, and the important thing about this that's different is that the velocities are 0 for solids. So we don't get a material derivative, we just get out this dt. Okay, so now we want to non-dimensionalize this guy. And so we can remind ourselves really quick of the geometry, the problem we were thinking of. So we had these two parallel plates that were different temperatures, but now there's no velocity, right? You try and shear a solid, it's going to push back, okay? Not a thing you want to bully around like a gas or liquid. And we're going to say T1 is greater than 0. And this has thermal conductivity and not a P, that should be a rho. I'm always looking for the eraser. Pull one from the other board. All right, okay, and a rho. Okay, and so now we need our length scale, right? And time scale and our temperature scale. Okay, and we don't need another scale here. We're going to just let this be. So our length scale is L. Okay, and our temperature scale, we've seen this before. Delta T is T1 minus T0. All right, but we have a problem in that we don't have a time scale. Right? We didn't have, before we had U that was shearing stuff, so we had a time scale, and now we don't have one. Okay, so what should we pick to be the time scale? I don't know. Okay, so I do know, but we're going to figure it out as we go. So I'm just going to let it be, all right, tau to be a unknown time scale, and we're going to see what comes out if we just let that go. Okay, so we can go ahead and define then our variables in terms of these scales that we want to. So we define temperature, dimensionless temperature, as T, and we'll just do divided by delta T, I think. Maybe I've done T minus T naught divided by delta T, nothing extra matter. We want to define our X as X over L. X is our dimension here, which in turn means that our gradients are given by L times the gradient, because the gradient has a d dx, right, in the denominator, so L comes up in the numerator. And we might as well make our time here divided by tau, this unknown time scale that we have yet to figure out. Okay, so we take those guys and we plug them back into our equation here and gather all the variables, and let's see what happens. So we are going to put, let's see, we'll do that rho C sub p hat, t, and then we have solve for this t, so that'll be t times delta t plus t naught. T tilde times delta t plus t naught. And then the numerator, I've got little t multiplied by tau. Okay, and that should equal k, and then I have grad squared. Oh, I need to put the L, that's fine. Yeah. I need to have that L squared grad squared. And then take the derivative of t, which is again t delta t plus t naught. Okay, so copy those guys up there. This derivative will take the derivative of t naught, that'll be 0. Delta t comes out and the tau comes out. So I get rho c sub p hat delta t divided by tau. Don't forget the important stuff. D t tilde d little t tilde is equal to, and on the other side, I have a KL squared, and then a delta t comes out of my grad squared t tilde.
Dr. Tree,
Yes,
shouldn't it be divided by L squared?
you're right. Thanks, Zach. Okay. So now I just need to multiply by this, the inverse of that term and collect. Right? So I have d t tilde, d t tilde. And now I'm going to have tau divided by rho c sub p hat delta t multiplied by k delta t over L squared. Grad squared t. Okay, so the delta t cancels. I get this one term, which is tau divided by L squared, k divided by rho c sub p. All right. So now what to do with that? So now what I'd like to do is I said we don't know what this time scale is, but I have a degree of freedom, right? Like I didn't pick the time scale, I could pick it now. What if I pick the time scale and make this equal to 1? If I say that's equal to 1, then what I can do is rearrange and solve for tau. Okay, let's say tau is equal to rho c sub p divided by k multiplied by L squared. Okay, well, do we remember what k over rho c sub p hat is? We talked about it. So when we talked about the Prandtl number, you're kind of staring at that. It's not the Prandtl number, it's the thermal diffusivity. Okay, so remember the thermal diffusivity has units, all diffusivities have units of a length squared per time, like a meter squared per second, something like that, length squared per time. So I can rewrite this tau then as thermal diffusivity, or 1 over the thermal diffusivity, length squared divided by the thermal diffusivity. So that means I've got length squared divided by length squared per time, which gives me a time and a numerator, right? So this is a time. So length squared divided by alpha is the time, okay? So what's going on here? So what I've ended up doing, sort of out of order here, I now have dt hat or dt tilde d little t tilde is equal to grad squared t. Okay, I just have a diffusion equation, okay, where the dimensionless number here is just 1. So there's no dimensionless ratio. But I have a different time scale. It's a time scale that comes out of a diffusion problem instead of the time scale that comes from convection. So in the Peclet number over here, right, I had to take into account conduction and convection. I had a time scale from convection and I had conduction. But here I only have a time scale from conduction. Okay, so I get tau is equal to L squared over alpha. Okay, and this idea here that there's a characteristic time scale of diffusion is going to be really important for us in the future of this class. Okay, and I think it's one of the most useful things I ever learned in transport, so I wanted to highlight this here. Okay, so what this tells me is that if I have, something diffusing, okay, there's a characteristic time that it takes to go that distance that it's diffusing, right? And it goes like the distance squared divided by the diffusivity. So if I want, to know, so if I put, some stuff here, and I look over here at time, later, I can either think about, or if I look at some length, I have some idea about when the time is that it's going to reach that point. Okay, this is the characteristic time scale. Now, if I want to know the exact time, it's, this is going to be proportional to that time scale. Okay, but I can use this to get rough estimates. Alternatively, I can also use this to find the length. Okay, the length is equal to the root of alpha tau. Okay, so if I want to know how far away something is going to feel diffusion, okay, at a certain time, I can pick a time and I can calculate that from, I can, calculate that length, right? And we're going to see when we go to solve problems like this after the exam that this quantity, length squared divided by the diffusion, or alternatively, some rearrangement of this, okay, will play an important role in having intuition for coming up with what are called similarity solutions, or a combination of variable solutions. Okay, so it's like a little preview of future. Okay, that's one reason why we talk about it, right? Okay, any questions about that? Does that make sense?
Why did you put one or
Why did I put one?
yeah.
Why did I say that was one? Okay, because there's no time scale here. Like there's like I put in a time scale, but there's nothing inherently in here that's giving me a time scale. So
So 20 0?
time scale 0?
Yeah, we don't have any time, so it should be 0.
Well, there is a time. I'm just saying that from the problem there's no other time scale. I don't know what it is. I could have told you. I could have said instead, how do I get a time scale? And I could have said, well, I have a diffusivity, right? I could have argued the other direction. I could have said k over rho c sub p hat is a length squared per time. And I could have said, let me pick my time scale to be, this, right? And I could have just argued backwards from that. And then I would have found that the dimensionless number was 1. Okay. I wanted to motivate it differently. I wanted us to see where this relationship comes from. So the broader point I'm trying to make is that there is a time scale here. It's the diffusive time scale. There's a time scale of diffusion, and that time scale is given by this, length squared divided by the diffusivity. Okay, but it maybe isn't obvious when you sit down here what the time scale should be. Okay, so if you have like an unknown time scale, if you know all the others, we could have done the same thing over here and let one of the things free and then picked one of them to be 1, and we would have found all the others. Okay, if we didn't know. And that's just a function of the number of degrees of freedom in a problem, right? And you can go back and use the Buckingham pi theorem. You guys remember this? And you can count how many dimensionless groups you should have. Okay, and if we went through and did this, we would see that we were going to have 0 dimensionless groups, okay? And that would tell me that I had to pick, this to be that way, all right? So like the broader question of how do I know, do I have a degree of freedom here or not, comes from the Buckingham factor. And that's just a matter of counting the number of variables in the problem and counting the number of dimensions that I have and subtracting them, if you remember that. I trust you remember that basic idea. Does that make sense, the Buckingham factor? If you don't remember that, if that's like, oh man, pit in my stomach, I have no idea what he's talking about, come talk to me and we'll go over it. I don't want to spend the whole rest of the class doing that, but I'm happy to review that concept. It's basically counting number of equations and number of unknowns with dimensions. That's basically where that comes from. So. Good question, though, Raya. Great question. Other questions? Unsettled about it? Be good. See Andrew nodding his head. Then I see like eyes staring at me. That's what I see. That's what I'm seeing. Internet people, are we good?
We are good.
All right. We got both Zachs today, or okay, Zach and Zach. I think ChEn thinks I like dimensional analysis too much. I think it's really useful. When you're a theory guy and you sit and do like the math all day long, and then you realize that there's this way that you can get like the answer to within a factor of 3 without doing any math. All you got to do is think about units. Yeah, I'll do that. It saves me all sorts of time. Okay, so do a couple examples. So the first one is here we'll do a solid rod with uniform heat generation. Okay, so let's set up the geometry. So we have a rod. This. I'll call that direction Z, that direction R. That means, let's see, ZR means our theta has to spin that way to be right-handed. We're going to say this is Z equals 0. This is Z equals L. We will call this out here R equals big R. We'll call the middle R equals 0. And we'll say that there is some source inside the rod. That source will be, maybe let's call that a source. It could be a chemical reaction. It could be electrical heating. Maybe it's even nuclear, but I don't know if nuclear will depend on space or not. So this we're going to say is not a function of our thetas. So this is just a constant source everywhere. Okay. So we're going to ask, what is the steady state temperature distribution? Or question. And we're going to assume that this rod, we'll make this a little more complicated than like the simplest ones we would do from the shell balances. We're going to make this rod embedded in a fluid. Okay, so embedded in a fluid that has a heat transfer coefficient H and external temperature T infinity. Okay, so that'll be the heat transfer coefficient. And an external. Okay, so first thing to do for these problems, right, is to write down the governing equations. Well, I think the first thing to do is to draw it. Think about it for a second. Okay, so we did that. We drew it, thought about it. We thought about our geometry. We labeled our various variables. Now we're going to write down our governing equation. So we just did these simplifications. So I don't think we need to start back at the nasty, equation of change for temperature and simplify. We already know what it's going to be for a solid. So for a solid, we get rho C sub E dt dt is equal to A grad squared T. Okay, but we need to add something else on because we didn't do it with a source before. So now we're going to have a source term. We add on a constant source. Okay, so we could go back to our energy balance and go through the whole thing. If you remember, there's just a generation term, okay, and the energy balance. We could throw S in. We could go through the whole last two classes, and we'll just end up with the S there, okay? But if that's kind of where you're wondering where to go, if you want to like think about it from very first principles, you can do the balance and get that guy out. Okay, so then we need boundary conditions. So in order to be able to solve this problem, we have our governing equation. That's not enough. We need to know what the boundary conditions are to be able to solve this. Okay, and if they were transient, we'd also need to know initial conditions. So what are our boundary conditions? Well, we talked about these a while back when we talked about solving the energy or the shell balance problems, right? We talked about all the different kinds of boundary conditions. And the ones I think that are useful here, I think this one was useful, unless I wrote it in the notes, so. We say that the temperature is finite in the center, okay? So often when we have these cylindrical problems, that's one that comes to mind, right? We saw that with pipe flow. The other one, which is the sort of dead giveaway that it's embedded in the fluid, is we're going to say that the Q at R equals big R. So the heat flux on the outside of our rod is going to have to be given by the heat, by what is that? Newton's law of cooling. T at R equals R minus T infinity. Which the heat on the surface of the rod, right, minus the stuff infinitely far away, and we'll plug our heat transfer coefficient. That's what our flux has to be. Okay. So now it's a math problem. From here on. If we say it's steady, we're going to neglect that term, right? The transient term. And so we'll say that 0 is equal to K grad squared T plus S. And we can write this out. We can rearrange this a little bit. Let's say we have grad squared T is equal to minus S over K. So now we need to take grad squared and expand it out and think about that for a minute. So let's do that. So in cylindrical coordinates, I get 1 over R d dr of R dr plus, and then that's 1 over R squared dt theta squared plus dt dz squared, and that's equal to minus S over K. Okay, so this, right, we should be able to use the table in the appendix to look up. We can't remember. I can never remember. I always get is it R, is R squared, is it inside the derivative, is outside? I just remember for cylindrical and spherical coordinates, I gotta look it up. Okay, so now we gotta think about this a little bit. So the first thing is that there's no term in here that gives us a theta dependence. Right? There's nothing in here. There's no like source term that depends on theta. So we can say dT theta is equal to 0 because there's no dependence in that in any direction. Okay? Okay, we need to be a little more careful about Z. Okay, so if I have a short little rod like this, right, then the temperature distribution is going to depend on the heat transfer at the ends as well as the sides. Okay, but if I have a really long rod, then I could just pick something in the middle and it shouldn't be affected by the ends. Okay, so that's the easy case. So let's do that. So let's assume we have a long rod. Okay, so we can neglect the ends. Or ends, they're always neglected. Okay, so in that case, dz is also 0. Okay, and we don't need to worry about that one. So we end up with 1 over r d dr, r dt dr is equal to minus s over k. Okay, so then from here, this is just looking like our shell balance problems, and we just need to separate and integrate. So let's see, put an r over here, cancel that one, and integrate, we get r dt dr is equal to minus sr squared over 2k. Okay, then I cancel the r there and there. And I can integrate again. And now I get, oh, I forgot a constant, plus C1. Now I get T is equal to minus SR squared over 4K plus C1R. I should have had that one over R, right? Okay, I'm going to make sure I say that so we get it. I canceled an R here. I should have divided by R in the C1 that I'd forgotten. So this should be now C1 natural log or natural log R plus C2. Okay. So separate and integrate. Now I need to apply boundary conditions. Okay, so the first boundary condition says that when I set r equals 0, this thing has to be finite. I have the natural log. That makes sense. Okay, so if I say t is finite, that implies that C1 equals 0. This is looking a lot like Poisson flow, right? To this point. So now I've got to find C2 as well. Well, this is where it gets a little bit different because now I've got this thing here where I need to know something about QR. Okay, so for this system that I have, QR is really simple. QR evaluated R equals big R is just equal to minus K dt dr evaluated R equals big R. So I can go back here, but I had dtdr right there, right? So I can evaluate that right away. I'll do it on this line. I can say this is minus k. dtdr was minus sr divided by 2k plus c1 over r. Better put that in parentheses so I don't screw it up. So now I get SR over 2 plus or minus C1K over R. And I still need to evaluate that at R equals big R. So that gives me S big R over 2 minus C1K over big R. Okay, and then I said that that thing has to equal H multiplied by T at R equals big R minus T infinity. Right? So I don't know what T at R equals big R. I also need to solve for that guy, right? That's, I mean, that is a temperature, but I have this equation here. So I need to plug big R into it to find this one. Well, I can do that pretty easy. T at R equals big R is equal to minus SR squared divided by 4K plus C2. Did I make, oh no. Okay, the other thing is I've been carrying on the C1, but we need to do that. C1 was 0. Forgot about that. That was silly. Don't need to worry about that, but it's 0. Okay, so now I should be able to solve for C2, right, in terms of this guy, because now I have T at R equals R, and I have the QR term. So we can plug that all in and solve for C2. So I get SR over 2 is equal to H multiplied by this piece here, minus SR squared over 4K plus C2 minus T infinity. So I should be able to just divide by H, move all the other stuff over, and I should find C2. So let's do that. So if I do it in my head, I get C2 is equal to SR divided by 2H plus SR squared divided by 4K plus T infinity. Okay, so now I get T is equal to minus SR squared divided by 4K plus, and then C2, which is SR divided by 2H plus SR squared divided by 4K plus T infinity. Now I should just be able to collect and simplify. So this is going to give me, see, if I have an SR squared over 4K, I can make this one a 1 minus R squared divided by big R squared. And then I get at the end SR over 2H plus T infinity. All right, I better check my answer, see if that's what I got. Oh yeah. And then an easier thing to do here too is now I can just take this and make this T minus T infinity equal to that. Give me something relative. I like that answer better. Okay, so intuitively, what's this saying? So I've got, this is kind of like the problem that we did the other time where I did Poisson and Couette flow together, right? Because in Couette flow, I have this source term, right? That's, for the velocity that's driving it, okay? So that's what I have here. Like if I didn't have this thing, I just have this linear part, right? Okay. That quite right? No, it's not quite the same because I don't have an R there, but I have this constant generation of heat coming from my source term, right? And then I've got this parabolic profile. So, I've got this temperature distribution that's parabolic, and that's all how much it is above T infinity, the outside piece, right? So at steady state, it's heating internally. I get this parabolic profile that's shifted up by some, ratio between the source term and the heat transfer coefficient. Okay, and then I've got T infinity outside. Okay, all right. So I think that was. So I had another example, but it was basically just to do some simplification, and then I didn't solve anything out. So the point I wanted to make, actually, that I'll just make right now with this other example, is that for this part of the class, okay, if you get to a problem and it depends on two variables, time and space, or two spatial variables, okay, I'm likely, or I'm almost certainly only asking you to just like have simplified to that point, okay, and not to solve it. All of this PDE kind of solutions of how do we get rid of this thing and make that thing into this thing with two variables, two independent variables, we're going to do after the exam. So your book, though, he likes to, Bird likes to kind of do these little tricks where he's like, oh, and we can get rid of this one and do this, and then he gets some answer out. And he's doing things like perturbation theory, where he's like, oh, this thing is small and we can do this. Or he's doing like a combination of variables, which we'll talk about, or these other solution techniques. And I personally find it kind of confusing. I think it's a lot better to just, at this point, get comfortable with the equations. So almost like all the problems that we solve end up looking like these shell balance problems, where we get out an ODE, you integrate twice and apply the boundary conditions, okay? And again and again and again. So if you ever like, if we're on the exam and you're stuck, right? And you're like, what do I do? Look around and see like, it's probably that I missimplified something and somewhere I should be getting an equation that just has one variable and I should integrate it and apply the boundary conditions, okay? So like all the stuff at this stage, like we're trying to make the math relatively simple and we're focusing on the equations. After the exam, we'll start to look at what's the different ways of solving these math problems and showing how in each of these different cases, we still get the same kind of math. And that's why it's useful to sort of think of these as one related thing. Okay? All right. So that's it. We'll do mass transfer next time. And good luck. Good luck with the homework.
I had a question. When you're talking about the